the space segment is probably the first place we think of when we think about a GPS or a GNSS system. And it's changed a lot, and we're going to focus mainly on the space segment when it comes to the U.S. constellation. But every single type of global navigation satellite system is going to have a space segment that's very similar to this. And that previously we talked about having at least 24 active satellites, and all those satellites are going to have unique IDs, and typically they're going to have a number associated with it. And with that particular unique ID, we're going to have a particular signal. They're operating around 11,000 nautical miles, or just over 20,000 kilometers above the Earth's surface, and they make one orbital period in just under half of a day, or half of a rotation of the Earth. So that means that particular satellite you're going to see at minimum twice a day, and that satellite's going to make that rotation in a little bit faster than one day, which means that every single day we're not going to have the exact same position of satellites, which is good. So we have different arrangements, and we get different signals and different positions in the sky depending on what day of the week, month, and year that we're actually collecting things. In addition to that, every single satellite's going to have some type of atomic clock that helps keep that satellite very precise down to the nanosecond. Originally, the 24 is what we started with in the Navstar system. In June of 2011, we expanded the system. They shifted some of the orbits of the 24 to be able to basically wedge in 3 more satellites in this configuration, which expanded us to 27 active satellites. And that was mainly because the U.S. Air Force was committed to having at least a 95% uptime on the navigation system, especially since we use GPS system much more than we did when it originally launched in the late 80s, 90s for operational use. And typically beyond those 27, they keep extra satellites in the sky that aren't being used, but they're operational. So currently, as of this early part of 2020, there's 31 satellites in operation in orbit. We're only using 27 of those, but those others are kind of hot swappable there so that they can be swapped out if need be at the last minute. And all these satellites operate on different frequencies, and they output different frequencies depending on the generation of satellite that they're looking at. But the 2 frequencies that we always see are what we call the L1 and L2 bands. You'll see these referenced as legacy frequencies. We still actually utilize them in some of the more modern satellites, but there are additional bands, L3, L4, and L5 frequencies that are used by those satellites also. And you'll notice that in the L1 and L2, we've got some C designations and M designations, and that has to do with the type of code that's being generated on these systems. But all satellites up until this point still offer those original legacy codes that were developed and output by the first generation of satellites. So what do we mean by the different types? Well, there's some legacy satellites. If we go back to the early 90s when we had that Block 2 satellites that we talked about, those came on, they had just the L1 and L2 bands. And those L1 and L2 bands, L1 was the only civilian band that was accessible code-wise by civilians. The military could access both the L1 and L2 bands. Those were replaced later by the Block 2Rs, or the Block 2R replenishment is what R stands for. And really, there wasn't a big difference between the Block 2As and the Block 2Rs. They really were just there to replace them because they only had about a 7-year lifespan, and they were reaching that end of that 7 years by the time that first one was launched in 90. And so they did basically provide a little onboard clock monitoring, but we still kept those legacy signals, and we still have 11 of those satellites still operational that are up there in the sky right now. Those were replaced by Block 2R M's, and the M just basically stands for modernization. And really with Block 2R M's is where we started actually adding additional signals and additional codes to the system. Still about the same lifespan, but in that 2005 to 2009 range, we started adding a new civilian L2 signal, which was a big deal because up to that point, to be able to use the second frequency L2, could only use the carrier frequency. You couldn't use any code on that. The military also got an upgraded M code, and there was some programming to allow flexibility of the power output on some of those satellite systems. Those eventually were basically replaced, or started replacing those, by the Block 2F, or what we call the follow-on series. There's still 7 operational satellites of the Block 2 RMs, and then the majority of our satellites, though, are kind of in that big chunk of the 2F follow-ons. So they have the same signals that came from the Block 2 RMs, and we added a third civilian signal, the L5, which is on a completely different frequency. They modernized things a little bit, advanced the atomic clocks, and increased the lifespan was a big thing when those launched in 2010. And that particular series has been carrying us along for the past several years, and then here recently they commissioned a new series, basically the GPS Block 3 and Block 3 follow-ons, which will come after the Block 3s are launched. And this introduced a basically fourth civilian signal, but still in that L1 range. So not a different carrier frequency, only 3 total carrier frequencies, L1 band, L2 band, and L5 band. But we added a new L1 civilian, or L1C band, in the legacy carrier of L1. And mainly the main reason for this was with all the new satellite systems coming on, like Galileo is a good example. They were changing how they were actually distributing the code and using the code. And so this L1C is supposed to basically utilize the same modulation method that Galileo and some of the others are using, so that you have some compatibility with newer model receivers. They can actually pick up both this L1C band and also be able to pick up those other satellite systems out there. The big thing with these new generation satellites is that they're going to have a 15-year lifespan, so they're going to last a lot longer up there in the sky. The other big change with the third gens was that they added some search and rescue payloads, what they call rideshare payloads, basically some additional things that are attached to the satellite. They're not necessarily used for the GPS signals, but they're used for other things. Instead of having to launch multiple satellites, they basically put all those features into one satellite. One is the search and rescue payload, which basically is a relay for kind of distress beacons and things that are on the either sea or air. It allows them to be relayed to towers across the U.S. or wherever it's needed to be relayed. And then they added a passive laser reflector array, which basically is an array that allows the control towers or the control antennas to actually reflect a laser back down to those control stations and get an exact position of where that satellite's at. And so we can monitor and basically keep that satellite in the correct orbit much, much better. The other thing that these had that's different than all the rest is the Generation 3 satellites now are going to come without selective availability. And we'll talk about what selective availability was as we get further on in this video series. So how do we actually modulate those frequencies? I gave you a set of frequencies for L1 through L5, and the simplest way I can explain how this works is we have a carrier wave, which is a particular frequency, and if we go to analog modulation, which we think of AM and FM radio as being a modulation of an analog signal, we have a signal that's, say, a low frequency sine wave like you see here in the little animation, and then we modulate it to show that change. So as that sine wave increases, then you see the amplitude increase. As it decreases, you see the amplitude decrease on that red middle signal. Frequency modulation, we modulate the frequency. We change the frequency as our signal changes. So as our signal goes up, we're going to basically increase the frequency. As it goes down, we're going to decrease the frequency. So you can kind of see that happening. And so amplitude modulation and all these types of analog modulations are things that we've been using for a number of years in the radio world. AM and FM radio has been utilized for a lot of different things. It still gets used today for a lot of those things. So here's amplitude modulation, where we have our message signal, we have our carrier signal at a particular frequency, and we're just basically changing the amplitude as we want to represent this message signal. In frequency, as I just showed previously, we have our same carrier signal, and as our message signal increases and decreases over time, we change our frequency to match that. The third type, which I didn't show in that original kind of animation, is phase modulation. In phase modulation, we basically are changing the phase of the actual wave that or the carrier signal, as we're trying to increase and decrease that phase, or that phase lag or lead time compared to the previous version of that signal, to give us that basically change, increase or decrease in the message signal. So for example, if we look at this dashed line sine wave, it is kind of lagging by 90 degrees behind this dark line frequency. So we think of every oscillating frequency as having 360 degrees worth of movement. As we go from 0 to 180 to 360 and return back to that same point, we basically rotated through a full 360 degrees. So we can think of comparing two separate waves as either leading or lagging by a particular degree. And so for phase modulation, we take our carrier signal, and we basically, as we're increasing, we're in some particular phase, and then as we start to decrease, we shift that phase and shift it by a certain amount, and do the same thing as we're increasing again, we shift again, and as we're decreasing, we shift again. And so you see these kind of like M shapes here, where we're making that kind of shift or quick change at the peak of our message signal. And so for analog signals like this one, we're going to be continually shifting those waves. But most of our code that we're talking about is a digital signal. And so digital signals, we typically take digital signals and we convert them, or we place them onto an analog channel or analog carrier, which is our carrier frequency, through a method called keying. And keying is just a term where we think about keying as if we think about keyboards, but really comes from a key, or a key for a test is a distinct set of numbers or answers for a particular set of questions. And so we think about the Morse code, which I've got pictured here, is a particular key that a particular letter represents a particular series of pulses. And so if we think about back to the use of Morse code and telegraphs to be able to create that, we don't care about whether the frequency ranges between this point and that point. We just care about the 2 points. And in digital signals, we care about a 0 or a 1, an on or an off. And so with keying, we're basically going to set particular points that represent zeros and ones, and we call that keying. And so we're going to use all these types of modulations in a shift keying. So amplitude shift keying, as you might think, is where we take a binary sequence, because we're talking about a digital sequence, so there's going to be a 0 or 1. So say we have this 0, 1 volt binary sequence, and to represent a 0, we do nothing to the signal, and to represent a 1, we increase the amplitude. And same thing here. So you can see how this amplitude shift keying is going to represent this binary sequence. Same thing with frequency. We basically adjust the frequency to represent each of those points. So we have a wave at a particular frequency. We change the frequency to high or low, and a high or low frequency represents the 0 or 1. Same thing with phase shift keying. This happens to be binary phase shift keying because we only carry about two solutions, a 0 or a 1, and so we can use two particular phases. And typically when you're doing binary phase shift keying, that means you're going to use 180 degree waveforms that are basically 180 degrees lag or lead from one another. So in the example here, we've got a waveform here that's at a particular frequency, that's moving along at that frequency, and then when we go from the 1 to 0, we shift it by 180 degrees, and we're still following that same frequency, and then we shift it by 180 degrees to get the 1, and then we shift it by 180 degrees to get the 0, we shift it by 180 degrees to get the 1, and so forth. And so since it has basically 180 degrees shift, one of the things about binary phase shift keying is we can actually encode two different messages on the same carrier frequency because we can use 90 degree offsets from one another and basically have four possibilities, a 0 and 1 for one particular signal and a 0 and 1 for the other. And that's what we use, and a lot of the legacy GPS systems uses binary phase shift keying, as well as the newer modern systems will use binary phase shift keying for a lot of those signals. So what's our actual signal, or the binary piece we want to actually send out? Well, that's that identifiable code or identifiable piece of that particular satellite, and we call it pseudo-random noise, or the PRN code. And basically every single satellite has their own PRN code. It looks like a bunch of noise because it's just a bunch of random zeros and ones. That's what it kind of looks like, but actually there is a distinct set of zeros and ones that every single satellite has, and that receiver that you're receiving, when it starts getting that signal in, it can decode it and realize, hey, this is satellite number 11 or this is satellite number 3 based off of this PRN code. And that PRN code is broadcast on two different channels, L1 and L2, and we call those broadcast codes, comes in three different ways. It comes in as a course acquisition code, or the CA code, which is on the L1 frequency. And then we have the military code, which is the PY code, which is on the L1 and L2 frequencies. And then the third piece is a navigation message, which is, we talked about how we can encode two things on the same kind of carrier wave. The navigation message gives some of that navigation stuff as to the time, where the satellite's at, where it's heading, and that kind of thing that we can utilize. So the CA code, or the course acquisition code, is a set of basically 1023 binary digits, so zeros and ones, and that particular set of 1023 zeros and ones is specific to every single satellite. So each one has its own pseudo-randomized noise there, PRN code. And it's transmitted by each satellite at a rate of basically just over a megabit a second. And it's transmitted on the L1 carrier wave, which is that 1575 megahertz frequency, using that binary phase shift keying. So we're creating those zeros and ones based off of that 180 degree phase shift. So this is the code that originally civilians could use because it was not encrypted, and it has a quick update because it's a very short code, and so your receiver can lock onto that and use that to actually calculate position and calculate distance. And we'll talk about that a little bit more when we get into the end user segment on how your actual receiver does that. On the other hand, the PY code, or the precise code, is a much larger code set than the course acquisition code. It's a little bit bigger than 720 gigabytes, which for the late 80s, early 90s, when this was kind of coming into existence, was a pretty big size amount of data. Instead of it just repeating like the course acquisition code that was just a little over 1,000 bits long, this one takes a week pretty much to transmit. So a satellite starts transmitting Saturday at midnight and then gets done with it pretty much about Saturday at midnight the following week. It's not a unique code like the PRN code is for the course acquisition code. Every satellite has a piece of this this code, this 720 gigabyte code, is a piece of a much larger master P code. And the master P code has about a 27 terabyte total size. So you take all the satellites that are transmitting, and they're transmitting just one piece of that. The P code's transmitted on both the L1 carrier and the L2 carrier at the exact same time. And since we're transmitting the course acquisition code on the L1 carrier, we have to do that phase shifting where we're shifting at 90 degrees offset so we can get two signals on the same carrier wave and not interfere with one another. And the military used this initially as a way to increase the precision of their particular units. They would use the course acquisition code, which was publicly available, to get a lock like we would normally get at this point in time. And then they would use the precision code to help tune that in and get a little bit more precision out of their system. Having two frequencies, as we'll talk about later, allows us to do some corrections for things like ionosphere changes and whatnot. So that's something that in the commercial world, we started using the L2 carrier, even though we didn't know the actual code behind it. We used the carrier wave as a way to determine those same types of corrections. Just we didn't have the opportunity to use that particular wave because it was encoded.